Hi, I'm Tom Carpay. I'm together here with Willem, Toorop, and Luc Hendricks later for the Q&A, and we'll be talking to you about our experiments into XDP. So our main motivation and goals were that programmable networks are quite hot at the moment, and for good reason. They offer flexibility in a data plane without sacrificing hardly any performance. And in this case, we specifically looked at XDP to perform some augmentation and tasks which can be done in kernel while still having traditional user space above that. Also, a fun fact about XDP, it can be hardware offloaded, but we'll get into this a bit later. So our main goal is that we try to augment the DNS, not replace anything and not write our own user space software. So I'll do a quick rundown of response rate limiting, or at least of incoming queries. I'm sure that most of you are well aware, but just in case. When you calculate the numbers, the queries per second for a certain IP source or prefix, you can calculate these, and when they exceed a certain threshold, you can decide to drop these or send them back with a TC bit, bounce them, and have them come back over TCP so you can track them. This is a common defense against DNS amplification attacks and reflection attacks, mainly for the victim. So the Berkeley packet filter is historically the virtual machine that handles your TCP dump filters. But ever since the extension in 2014, it's a much more powerful VM that offers you flexibility in arbitrary code ran by the VM in kernel space without having to reboot. One of the network driver hooks that BPF offers, it's the express data path, or XDP, which is what we're looking at here. The main benefit of the XDP is that it executes, that a program is executed right before anything hits the network stack. It can also be offloaded from networking, as I said before, hardware offloaded for the networking, and that we can have it not allocate buffers, which is where the main performance benefit comes from. Also, I put DNS, the domain name system, here as a bit of a joke, but it is relevant as it is quite important because we don't try to modify DNS in that sense. We only try to augment a specific feature of it. So this is a classic in-kernel network stack where a packet comes in through the network interface card, the NIC, then is off to the driver space, then traverses the network stack, eventually to end up at the socket where a user space software can interact with it. When you add XDP, which lives somewhere around driver space, the XDP program decides something for the packet, the destination, if you will, right before it hits the network stack, and is handled by a higher laying user space software, such as NSD in our case. One of the things it can decide is to just pass the packet along to the network stack. It can decide to bounce it, so to redirect it back to the same network interface as it came from. It can decide to drop the packet, which is quite self-explanatory. And then it can also redirect it back to another network interface. The last case, something we don't use, but is nice to mention, is that it can decide to bypass the network stack entirely. And that offers the flexibility of, or actually even the performance increase of having to bypass the network stack, and therefore negating that performance hit. So in this work, we try to augment DNS. So add a functionality. We didn't modify any any DNS user space software, and we didn't bother implementing any XDP bypasses or something like that. So now you may ask, how do you get such a nice program running? Well, first you have to write some C code, compile this, and then you have a program which you can attach to a network interface. You can do this via the IP link command. And then you encounter the dreaded dreaded verifier even. The verifier is there because you're trying to run arbitrary code in kernel space, which can be quite insecure. So to make it slightly more secure, the verifier checks things such as, does the program terminate? Is it not too complex? So within 1 million executions, and does it stay within memory bounds? Well, if you're very lucky and you did a good job, then it finds no objections and your code is now active on the interface. And every time that interface gets a message on ingress, so a packet on ingress, then it processes, the BPF program processes this packet before and decides what to do with it, so it can send it along to the network stack, for example. Once you attach a BPF program, it doesn't really offer any flexibility in terms of interaction other than via BPF maps, which we'll get into later, which have to be programmed into the program, the BPF program, that is. But as you can see, there's no mod probes, no rebooting of the software, no reconfiguration of user space software. It just works. Our algorithm for response rate limiting, from which the code is on GitHub, first checks if an incoming packet is a DNS packet. So it checks the headers and the port, and also makes sure it's correctly formatted. And if it's not, then we just send it up the network stack to the DNS software, user space software, to figure that out. But if we are dealing with a correctly formatted DNS query, then we can calculate the queries per second rate for this specific source address. We can store this in one of these maps. And based on the QPS rate we calculate, we can decide to either pass along to the network stack the query, and then we apply no rate limiting, or we can, depending on configuration, drop the packet or bounce it with the TCP bit sent, and then we do response rate limiting. So BPF maps are arbitrary data structures that are specific to BPS. On the left here, you see all the options that there are currently. Note that there are some per CPU to negate blocking behavior. And then also note that some of these can be hardware offloaded, but that's something maybe for the future. So the map we use to do our response rate limiting is a hash map. This hash map keeps state in between packets using BPF maps, because the program is run again and again for every new packet that comes in. So the key of a hash map, of our hash map even, is the source address of all the incoming queries, and a value is a bucket, which we can see on the right here, stores the number of packets and the start time of the frame, so which you can use to calculate the QPS rate, and you can then decide to response rate limit or not. Well, we also had an operator request. We'd like to do response rate limiting, but not for a group of VIPs, if you will. This can also easily be done. For this, we use another data structure, the LPM tree, still with IPv4 and IPv6 keys, and then a value as a hit counter. So if this source IP address is found in the tree, then we just bypass the whole response rate limiting and just XDP pass. So the user space software can actually respond to this query. Excuse me. The nice part about this is that it can be accessed from user space with a BPF tool or even a self-written tool, and that you can, after the fact, after you attach the program, still include or actually declude if you wanted to, some prefixes as your heart desire. I will now give over to Willem Toorop to do the demo.
Top. Then you have to stop sharing your screen so I can share mine. Thank you. Okay, first I'm going to share my terminal window, which is this one. Can you see my terminal? I assume you can.
We can't see your terminal.
You cannot? What do you see then?
We can now.
Oh, you can. Okay, excellent. So I've, live demo. Started a virtual machine, which is running a name server. I can send it a query like this. And you see it's responding. And suppose you are running this name server. This name server is yours, and it's being misused in a DNS amplification, reflection, denial of service attack. And you saw this presentation, and you think at the UKNOF, why don't I try out this work that Willem and Tom and Luc presented? So I will now secure shell into my name server. And I'm going to show you how to use our work from scratch to experience by yourself how low the barrier is really to start using this stuff. It doesn't matter what kind of DNS service you're running. It doesn't have to be NSD, unbound. You did not have to anticipate it. It just, you can use it at any time, as long as you're on a Linux box, by the way, because that's the thing that's running XDP. So this is the repository. It has a few directories. This work has been used in the context of a blog post. A series of blog posts, actually, in which we explain or tell about our experiments of XDP and DNS. And the first blog post was about just replying refused in XDP, right? So that's the DNS says no example. And the second blog post was response rate limiting, which is the RRL directory. And the third blog post will be about fully fledged DNS augmentation in XDP. And cookies and padding are part of that, but we haven't published this yet. So because we are using a userspace program for the very important prefixes, I have to compile this library first, but that only takes a moment. And then I will take you in the response rate limiting directory. And in the blog post, we explain it to you gradually how it works, right? But the fully fledged response rate limiting implementation is in round 3. So let me show you the C module. So at the start, it has all kinds of defines that configure how the rate limiting will be done. So it's now configured to rate limit to for prefixes of /24 for IPv4, /48 for IPv6. And then it will be subjected to rate limiting if by default queries per second increase to above 200. But for the demo's sake, I will change this to 5. Also, this very cheap virtual machine has only 1 CPU. I have to anticipate this as well. And I will set the slip rate to 1. Which is convenient. Then every packet that will be rate limited will be returned with a TC bit on, telling the requester that to return over TCP. Okay, so I just make. I also have to make the VIP maps. No, make to communicate with the program. Then I can do load. And now our response rate limiting is loaded. So let's send a query again. uknof.org/UKA. I want a short answer, and I also say ignore to not return over TCP. So let's do this more regularly, and also show that we are sending queries with half a second intervals. So 2 queries per second are answered, but if I increase this rate to a lot, then you see that some are answered, but most are not. Only 5 per second are answered. The QPS that I configured. Oh, I keep this running. Oh no, yes, I keep this running. So now we'll use the userspace tool to add my IPv6 prefix from which I'm sending the queries. You can add prefixes, delete prefixes, export and import them, which is 2NL4. And you see that every request is now answered again. So I will talk a little bit about cookies later as well. So I just want to quickly show you the kernel part of DNS cookies, because it has all the options that we had for response rate limiting. But in addition, it also has the cookie secret that can be configured. Okay. I stop sharing this screen. I start sharing my slide deck. Can you see my slides?
Yes, we can.
Thank you. So what have we learned from all this? We can augment existing DNS servers regardless of the software that it's running to deal with incoming DNS packets. So stuff like access control or dealing with denial of service attacks. You can decide to deploy it at any time. You did not have to anticipate it beforehand. BPF Maps can be used to maintain some internal states, like for rate calculations, but can also be used to communicate and configure the XDP module from userspace at runtime. Which is what we did with the prefixes that need to be excluded. So if we talk about rate limiting, we have to talk about DNS cookies as well. So I showed you in the demo how to add prefixes to exclude from rate limiting. So DNS cookies are a way to learn which prefixes to exclude automatically. So how does that work? Well, remember that in a reflection amplification denial of service attack, the attacker spoofs the source address of the victim. The attacker pretends to be the victim, and she never receives the answer from the name server herself. The attacker sends the request, and the victim receives the answer. So if we could recognize a returning client somehow, we would be sure that its address is definitely not spoofed, and we could exclude it from rate limiting. And this is precisely how DNS cookies work.
Hi, Willem. Portia.
Yeah. Hi, Portia.
Just to let you know, you've got 5 minutes until Q&A.
I'll do my best. So cookies are a bit like a TCP handshake. The client sends a cookie. In the request, the server creates a server cookie, basically a hash from the client cookie, the client IP, and the secret known only to that server. And on all subsequent requests, the client sends along this server cookie. And the server can then check it's a returning client, because the server cookie the client presents could only have been generated by that server itself, with a secret known only to that server. So does the server see a valid server cookie, return large answers, do not do rate limiting. And the spec to describe how to do this interoperable is RFC 9018, which has just been released 9 days ago. So XDP is running in kernel space, so we cannot use all the convenient libraries available to user space programs. We can't use libcrypto from OpenSSL to calculate a hash. But luckily, the proof of concept implementation of zip hash for DNS cookies was directly usable without much modification. You only had to replace the variable length variables to fixed length variables to make the function digestible for the verifier, and that just worked. And so we have an implementation of DNS cookies verification in the XDPerienced GitHub repository, which works as in this picture. So the XDP module first parses IPv4 or IPv6, and then the UDP verifies the cookie. Is it a valid cookie? Is there a valid server cookie? Redirects directly with XDP pass to the user space program, and otherwise send it to rate limiting, which can check it or reply with TCBit or send it up. But then note that the response, the creation of the server cookie, is still done by the user space software. So it's a bit of a half-baked implementation, because DNS cookies are not just about verification, but they also need to be created. So we still need the user space DNS software creating the cookies. So the secret to create cookies and verify them needs to be in the XDP module and also in the user space DNS software. So is it worth it still to do cookies in XDP as well? Well, yes. You have to do it. If you're doing response rate limiting in XDP, then you have to do the cookie verification in XDP as well. And even though you have to configure the secret at 2 different places, it's done before anything else, before socket buffers are made, etc. But could we have made a fully fledged DNS cookie implementation? Yes. So this is what a fully fledged implementation would have looked like. There's no outgoing XDP layer, but there's an outgoing TC layer. And TC stands for traffic control, stuff like traffic shaping, quality of service. At the TC layer, network packet is in a socket buffer, which is way more flexible to work with. But you have to associate those BPF programs at the XDP and TC layer. They are 2 completely different programs that do not share anything. To associate incoming with outgoing packets, you have to use a map. So all incoming packets need to be registered in this map. And when they go out of user space to be sent out on the network again, the TC BPF program at TC layer has to look up in this map what to do with the packet.
Hi, Willem. It's Portia again.
Yeah.
You are now in your Q&A time.
Yes.
Just to check with Leo if you have just a little bit more time to continue or not. Leo?
We have one question in, but there's probably enough time to answer that and to just finish up.
Yeah. Okay, so I just want to show you that this is possible, but we did not do it for DNS cookies, but we did do it for padding. So because is it still worth it to do it this way? From a performance perspective, maybe not, because at the user space layer, you do not have registration of incoming queries and lookup of outgoing responses. You just read the incoming packet, do the look up the name, create a server cookie, or reuse it and send it out. So there's it's better to do it in userspace. We consider it better. But as a proof of concept that it is possible to do a fully fledged DNS augmentation, we created padding. So we had padding implementation in Unbound for DNS over TLS, but it doesn't. But we had a user who was offering DNS over TLS, or an operator actually. That's not called a user, and he used DNS dist, and he had a backend pool of Unbound resolvers, but he used DNS dist to do the DNS over TLS. Now, he communicated with Unbound over UDP, because he wanted to have the padding option in UDP. And while we didn't want to do this in Unbound, because we don't want to reply with large packets over UDP, we managed to use this technique of registering incoming packets and associating that with outgoing packets, and create a little XDP BPF program to do the padding, to augment existing DNS servers. Didn't need to have to be Unbound either in XDP. So I think I will now skip to the conclusions. So a lot is possible. XDP and BPF is a very good fit for plain old UDP-based DNS, because there's per packet processing, less suitable for TCP. But we think that using XDP to augment the existing DNS server is an exciting new idea and a great new tool in the DNS operators toolbox. So in the future, we are looking currently already in offloading to hardware. There are network cards that can run XDP programs. We're looking into statistics logging, sending the packet right up to the userspace DNS servers. Hot self-managing cache, I love this. So at the TC layer, register the outgoing packets, store that in a map, and then on the incoming XDP program, see if it's already in this map, and just answer the query from the XDP, which would be a very nice feature. Load balancing and the root zone from XDP is also on our wish list. So maybe I can answer a question in the minute that we still have.
Yes, thank you very much, Willem. So I'm going to read a question in a moment, but while I do that, Dinesh is going to pop up the poll, which is how we gather feedback on our speakers and talks. The question comes from Kathy Armand, and she asks, "Hi, Willem and team. This is great, but to me it looks like query rate limiting rather than response rate limiting, unless I'm missing something. Can you confirm?"
Yes, we are rate limiting the incoming packets, but this kind of rate limiting is actually looks more like response rate limiting. Because so normally response rate limiting is named like this because you do not want to return large responses to people you don't know, right? So different software can also set different query per second or different rates for different responses, to have a different rate for actual answers than for errors or non-existent domains. But it's still about the incoming request that will be, for which a response will be sent or not, so to say. So in that sense, it's known as response rate limiting. And I don't know how ISC calls it, but we also have query rate limiting, but that's what we call limiting the query sent by the recursive resolver to the authoritative. So for us, that's quite a different thing.
Thank you very much. That was lovely. I'm going to hand back to Keith now.